Hello, everyone. Welcome to the Transformative Vertical Flight Working Group Public Services meeting number 89. Today is Thursday, August 22nd, 2024. My pleasure to be able to have a invited speaker, Devin Boyle from NASA, to talk about the NASA Advanced Air Mobility Vehicle Research. It's one of the best presentations I've seen that's comprehensive across the board, give us a big picture understanding and with enough detail. So I'm very, very much looking forward to this whole presentation. Before I introduce our speaker in a little more detail, let's go to our regular topics. Just for looking forward, a few meetings coming. One is the Commercial UAV Expo, September 3rd to 5th in Vegas. And co-located is the Flying HY, the hydrogen expert get-together meetings and so on that co-located with the Commercial UAV Expo. Also, we have the in Canada, we have AAM 2024. It's ICAO's first Advanced Air Mobility Symposium taking place September 9th to 12th in Montreal, Canada. That will be a pretty worthwhile meeting to engage. Also of significant interesting topic, the 8th AAM Infrastructure Workshop going to take place in September 17th to 18th. And also we have the European Rotorcraft Forum 2024 coming up as well. There's also another one in case everyone got interested in flying a little further away from most folks' hometown. There's Air Taxi World Congress going to take place in Dubai in October. Those are some of the forthcoming. There's many more. So please, everyone, if you have new and interesting activities, coming meetings and events, send me an email. I'll make sure we're including each month as look ahead. Just for a note, next month I'll be traveling overseas. So the meeting will be planned out, organized, and conducted by Dr. Pavel. Our co-lead of this working group, and looking forward to that. I will do my best to log in wherever I may be. Now back to the our speaker today. Devin Boyle is currently the electric vertical takeoff and landing eVTOL propulsion SubProject manager in the revolutionary vertical lift technology project within NASA's Aeronautical Research Mission Directorate. Devin began his NASA career as a corporate co-op student in 2007 at Armstrong Flight Research Center located in Edwards Air Force Base in California. His technical background, including turbofan propulsion integration, flight tests, and research at Armstrong Flight Research Center at Edwards Air Force Base, as well as turbofan and electrified aircraft propulsion acoustic research at Glenn Research Center in Cleveland, Ohio. And also of very important interest for everybody to know, I'll let Devin introduce himself a little more in detail, but he's active pilot and flying the Cessna 182s and the Grumman American Yankee. I think many people are familiar with those airplanes. And that can be illustrated by the fantastic photo show on this page. Now, without further ado, I'm going to let Devin take the floor and tell us all about the NASA eVTOL activities and more.
I would like to ask, I guess I should have asked, I see the topic here being public service. What's the background of the audience?
We actually, even though it's coordinated by the so-called public service working group, the working group really has two primary focus. One is for commercial AAM activities. The second part is the more focus on UAM related topics. The second segment that we focus on is the public services, all the potential use cases, challenges, opportunities, solutions, leveraging eVTOL AAM advancements. The audience are from everywhere. We have folks from technology side, from OEM manufacturers, supplier, tier 1 and 2 suppliers, as well as end users, the like fire chief, EMS operators, and government engagement, including FAA, SAE, and other organizations. So it's pretty broad-based, and we even have folks in the legal professions as well as infrastructures. So it's a
Wow.
very
Okay.
broad-based audience base. And because when we send out the meeting invite, we do not separate which focus on the working group. All the working group members gets invitation, so everybody can select whichever meeting is of interest to them. So you got
Okay.
a
Wow.
pretty
Yeah.
broad-based audience here.
All right. Excellent. So I'm going to share presentation in presentation mode. Can you or others see it? It's indicating I'm sharing.
Tom, are we good?
Yeah, I can see it.
Good deal.
Okay.
Yeah, this is Mike.
Okay. And I apologize. It's ironic. I work from home now more often, and so when I go to work, I'm hoteling, so to speak. So my home setup, I have better lighting on my face and everything. At any rate, hello everyone. I'm Devin Boyle. Irrespective of the mouthful title that you just heard, kind of the basis of what I do now in my current role is manage technical work across what I would call vehicle-centric development, focus on the urban air mobility mission primarily. So that's the 4 to 6 passenger people carriers. Urban air mobility is a tagline. It's not exclusive for the use case for these types of vehicles. And so I'm going to be talking, I'm going to start with a big picture of NASA's Aeronautics Mission Directorate and then kind of drill down from there to show how my particular project and others work in the AAM realm and how that fits into the bigger aeronautics picture. All right. Okay, so big picture, NASA Aeronautics. When we talk about mission directorates, I try not to make the focus on NASA's internal structure. That's not really all that interesting and necessary. The point of that really is just to say that NASA has very big, broad missions, and that is aeronautics and various aspects in spacecraft operations, spacecraft development, as well as a science mission directorate. So this is the aeronautics piece, the so-called first A in NASA. So 4 big picture thrusts, if you will, that NASA has in developing ultra efficient airliners. And so you can see there a rendering of what we have internally called a transonic truss braced wing. This is basically a modern take on the tube and wing aircraft to make it far more efficient than its predecessors. And NASA has recently signed a contract with Boeing to develop what we're terming the X-66A, so an airliner X-plane. Maybe not as exotic as the days of yore when we were doing super high, supersonic lawn darts, but this is the new world of sustainability, of making things more efficient. Additionally, we have work in the broader integration of more vehicles into an already congested airspace. So the focus there is on digital technologies enabling sort of a future iteration of airspace management, because ultimately air traffic controllers aren't going to be able to operate, manage so much traffic, and they're going to need solutions that help supplement that while maintaining the high level of safety that the U.S. consumer, the flying public, has come to expect. So high-speed commercial flight. We just recently, I don't know if celebrated is the right word, but we're just over 50 years since supersonic flight over land was banned. And certainly it was the case that the only commercial supersonic aircraft, the Concorde, was relegated to flying a London to New York and Paris to New York route to take advantage of its incredibly high speeds. So NASA is revisiting this challenge and trying to shape the sonic boom in such a way that it doesn't coalesce and become that really sharp, jolting, disrupting sound that you might hear from a supersonic aircraft. And that could potentially lead to, again, a future market where passenger carrying airlines are able to much more quickly traverse the continental United States and beyond. And so finally here with advanced air mobility. So this is a very, very broad topic, I'm sure, as you know. This encompasses everything from the vehicle level, for which my project has a focus, to the infrastructure, where and how are these things going to operate in the environment in which they're intended to operate. Excuse me, and then the airspace, right? And so there are a total of 7 NASA projects that cover this realm of advanced air mobility. And as I said, our focus varies from the vehicle itself all the way up to operationally, how are you going to use these things and operate them safely in an already congested airspace. So this is a kind of widely shared sort of NASA graphic. And the basis of this really is to indicate that, you know, we have this sort of generic topic of advanced air mobility and urban air mobility. But the reality is the electrification of aircraft and what we call distributed electric propulsion. So that is having many motor and rotor pairs all over the vehicle is something that's kind of unique and has come to bear with the improvements in battery technology and the implementation of electrified propulsors on these aircraft. And that really has opened the design space. So now we're able to envision economically viable designs that can operate in many different capacities that, again, were once possible, but seldom or if ever economically viable. And again, that extends not just to urban operations, to the so-called air taxis. That really also extends to, again, as the name of this working group, public good missions. So we're seeing companies now developing aircraft that have this vertical takeoff and landing capability, a la the HEMS or helicopter EMS type of application, but they're much simpler to operate, potentially even automated. And so now you can consider bringing someone to bear on an emergency medical situation whose primary role is not to be a pilot, but rather who is being conveyed there in a vehicle that was once prohibitively expensive and complicated to operate and required a commercial helicopter pilot. And certainly this extends also to unoccupied or uninhabited aircraft as well. And so some obvious use cases there are bog standard cargo delivery, certainly time-sensitive cargo delivery, sort of intracity time-sensitive packages, and many other opportunities. The hilarity of the what was it, the burrito bomber and the taco copter delivering your food. So, you know, there really are again a lot of unique and new opportunities availing themselves with these new vehicle designs. So that's great, but it comes with a caveat, right? We we love the innovation. We love this sort of disruptive market and the potential that comes with it. But the caveat really is that we need to implement this in a way that is safe, efficient, and is not affecting the non-flying public or the non-participating members of the public. And so in that vein, again, digging down now further to the project that I represent, the focus that here will be from here on out on the vehicle itself and what NASA's role is and what we're doing to ensure that these vehicles are going to be operating safely, quietly, efficiently. And so in that vein, we have a number of different research areas within our project focusing on those very aspects of vehicles. And again, this is now the subset, particularly of what we call UAM, or this sort of 4 to 6 passenger, people carrying, human rated type vehicles. The vast majority of them are expected to be vertical takeoff and landing capable, and either fully or partially electrified as in a hybrid configuration. And so this is just a snapshot of all these, and I'm now gonna kind of dive a little bit deeper into each one. Okay, so first one I want to talk about is the motor or the powertrain and power distribution system itself. It's certainly true that again, what we call distributed electric propulsion has enabled inherent redundancy, right? So now you don't have a helicopter with a single main rotor and maybe 2 engines. Now you have 6, 8, 10 rotor systems that each have their own propulsor. So that's great. That sort of this electrification has enabled redundancy just on the basis of distributing propulsors all over the aircraft. But that is not where we stop and declare success. These things can and do still fail, and that causes controllability issues, certainly passenger comfort and acceptability issues. And so we're implementing research to take this a step further and improve the reliability of the propulsor itself, and have built up facilities to that end. So NASA research now is looking at motor architectures, electric machine architectures that have internal fault tolerance and actually have sort of internal redundancy within a motor, not just saying I have 10 motors on this aircraft, it doesn't matter if one fails. So pushing that state of the art and improving the reliability of the motor itself, of the propulsor itself, is one of the major ways in which NASA research is helping to push the state of the art and improve safety of the overall vehicle. Additionally, it's certainly not trivial to push 600, 800 volt, 1000 volt DC power everywhere. That comes with many consequences to what we call power quality. So you can think of EMI as being an obvious one, electromagnetic interference. And so NASA has built a facility and has been working different aspects of the power quality problem, if you will, trying to understand the nuances of that. And from that, NASA data has directly contributed to, and our researchers have directly contributed to a high voltage power quality standard, as well as a motor specific permanent magnet motor performance standard through the SAE standards committee. And so those again are going to help industry to use an accepted and established standard for vehicle power systems architecture development, as well as helping the FAA in the daunting challenge of regulating these vehicles that don't look like anything that we've seen before. So in addition to the safety issue, noise is a major concern, and so he alluded Johnny alluded at least a little bit to my background, and coming from acoustics and from a sort of propulsion flight test background. This is, I'm happy to see something that is a front and center issue with this new market of aircraft, because historically we've developed aircraft and they were typically incredibly loud, and we only subsequently came up with band-aid solutions over decades of research to make, for instance, fan and jet noise on turbofan engines quieter. And we continue to this day to work on those problems because, again, the non-flying public, the people beneath these flight paths, have to deal with this on a daily basis. So NASA research now is helping to get ahead of that problem with these vehicles, and is working to develop tools so that manufacturers can do trade studies between performance, vehicle performance, so they can meet their performance metrics, and the noise generated by the vehicles themselves. And in developing those tools, we need to anchor ourselves in reality. And so that really is makes it necessary to do actual component level wind tunnel tests, as is shown here, a number of different tunnel tests focusing on different aspects of the noise generation mechanisms, so that our tools are physics-based and that they're accurate. And in addition to that, taking it a step further, we have a component of high fidelity tools as well. Again, digging deeper into in that design chain from very broad conceptual design into a more detailed design analysis of various designs that vehicle manufacturers may be interested in pursuing. Okay, so again, sticking with that theme of noise, we've also got researchers focusing on assessing fleet noise. And again, this is not just a single vehicle, but now operationally, if these things want to have high density operations, what is that going to look like, and how are these going to affect people? Some great anecdotes here. The current sort of state of the art of vehicles, and I certainly can't name any names of vehicle manufacturers, but these aircraft are already significantly quieter than traditional rotorcraft in their operations. The issue comes into play when you consider how they generate noise. One of the major challenges is that these vehicles have many rotors, and those rotors all generate their own tones, and then there are interaction tones. Humans have a natural aversion to tone noise. And another sort of squishy challenge, if you will, a subjective challenge, is that these vehicles are new and the way that they produce noise is different, and people have trouble accepting something that's new and doesn't sound the same as what they're used to. A good example of that is we have a facility at Langley Research Center called the Exterior Effects Room, and they can synthesize with many surround sound speakers the sound of an aircraft flying over, or in this case, a sort of delivery diesel box truck. The box truck being at 90 decibels, say, so fairly loud, but broadband. And this little delivery drone coming up to your porch and dropping off a package, 20 decibels quieter. So this is a logarithmic scale. So we're talking significant reduction in the amount of noise that this drone generates, or this uninhabited vehicle. But the subjects that were brought in from the public, when exposed to these two different noises, rated that drone to be far more annoying than the truck. So it's not enough just to capture how loud something is in terms of level. We have to capture the subjective human response. And that's a major challenge, right? So by its very nature, how do we quantify a qualitative subjective response? So we've got groups that are working very hard to develop a model of the annoyance that people experience with these vehicles. This so-called psychoacoustics challenge of quantifying how humans react to various noises. And in that vein have developed tools and implemented them in well-established environmental impact tools like the FAA's Aviation Environmental Design Tool. So crashworthiness is an inevitability. As safe as we make these vehicles, things happen. And so we've got a group focusing on developing standards, developing simulation tools so that vehicle manufacturers and the FAA can evaluate the crashworthiness of different designs. And in fact, you can see there in the image up there, and you can actually see a video on YouTube of a fuselage with various seat designs, with the high density sort of lithium ion battery, kind of state-of-the-art battery incorporated into the structure, and how that cabin crashes, and comparing that to a simulation that NASA developed with accurate, not just weights and mass distributions, densities, but also developing higher fidelity material models to accurately assess the crashworthiness of different composite materials, since they're much more common in these vehicles now. And so again, the broad picture here is NASA developing tools, and NASA is developing consensus standards through established standards committees like the SAE. And in this case, in addition to the vehicle level crashworthiness, we have researchers also evaluating bird strike impact tests, and even as sort of an aside, developing a surrogate bird model for bird strike testing, so that you don't have, forgive the crassness, but the mess of testing with real birds, and so that you can get more repeatable data, since birds are biological systems and they vary from one to the next. And so again, advancing the industry state of the art in various companies with various resources, with their ability to test in a manner that meets the FAA's requirements for bird strike. Additionally, performing drop tests for batteries, evaluating battery placement, battery impact and survivability, and particularly with respect to the well-known issue of lithium-ion batteries and the so-called thermal runaway issue. Sorry, there's my insulin pump beeping there. All right. So on to ride and handling quality. So ride qualities you can think of as a passenger issue. Handling qualities being a piloted aircraft, pilot-centric focus. And so our groups, again, developing recommendations and standards, but also developing a set of tools and validated data sets to enable manufacturers to build vehicles that are going to be safer to operate for the pilots, with respect to very complicated control systems. No matter how you approach your control system, with a cyclic or collective like a helicopter, or with variable RPM control, the issue pertains to the fact that, again, you have 6, 8, or 10 controlling rotor systems rather than a single main rotor now. I like to characterize these vehicles as sort of jittery compared to helicopters, because they have so many different rotors that have very quick responses, thanks in part to their electrified propulsors. They can respond much more quickly, and so the vehicle dynamics are very different than how helicopters operate. And so our teams are trying to understand this, trying to quantify it, and build tools that help build these things to be smoother, safer, more effective at controllability. So bringing it all together, I alluded to this already, but the research that we do is not just serving of private companies who are building air taxis for large urban environments. There really are many opportunities for what we term public good missions and applications that were once not economically viable with the electrification of aircraft, either fully electrified or hybrid. And the sky's the limit. We continue to see companies dreaming up new use cases for missions, like the one I alluded to, where a private company is looking at a rural first responder mission with a small electrified vertical takeoff and landing aircraft. So again, there are so many opportunities now that are being enabled, and the research that we're doing is really helping to make the broader industry have the tools they need to make the vehicles safer, quieter, more efficient. That's my elevator line there. And then I think that's pretty much it. Just coming back to the NASA aeronautics focus, and then RVLT, a subset of that, advanced air mobility research being particularly focused on the vehicle itself. And then NASA has many other projects that are focused on challenges with operations, infrastructure, airspace, communications. And that's it.
Thank you, Devin. Anybody? Yeah, let's. We have time for some question and answers. Let everybody feel free to either raise your hand or just go ahead, turn on your microphone, video, and talk. Hey, Devin, while folks are thinking about questions, I do have one. You were talking about the not just a simple equation of the decibel readings of a particular type of vehicle, like the eVTOL may be already significantly quieter from the data perspective than the helicopter traditional vertical flight machines. But I'm thinking about what one of your charts you're showing that the if a urban air mobility air taxi business are in place, dozens or hundreds of flights per day in from some selected vertiports.
Mm-hmm.
Is it, in your view, feel free to guess, you don't quite have the full answer yet, would it be better off in some cases to fly a fixed path so that folks live under the flight path got used to that noise, like what you talk about? They felt the drone is more annoying than the truck. If we brainwash them over the next 6 months or a year, are they going to get brainwashed? And if we fly everywhere, dynamic AI-based flight route planning, avoid repeated route, is it worse? Which is better?
This is a great question. And so you may have heard this anecdote. We participate in NASA's acoustics technical working group, and there's now a spin-off of that, the Urban Air Mobility Noise Working Group, whose focus, as the name implies, is on electrified vehicle noise. We have a large Class Bravo major commercial airport noise manager that comes to these meetings, and her statement was, we have 1,600 noise complaints a year, and 1,200 of them come from 2 people. So we're not going to please everyone. It's just the reality that there will be people that are that cannot be placated. However, you know, when you mention that, as it happens, this is something that we're actually seeing because with the advent of ADS-B and precise land-based, sort of land-corrected GPS data, we can actually fly aircraft in a manner that is far more repeatable than we used to with radio navigation aids. As such, we're seeing very tight flight paths over cities, and consequently, we're seeing a much larger exposure rate to the people under those flight paths, but a much more shrunken exposure area, right? And that's exactly the problem that you're mentioning. Honestly, it's hard to say which one's better. Do you really upset a few people, or do you spread the upset around? I don't think that either of those is a good solution, and I think that's why the noise problem is not stamped as being solved for commercial aircraft either. We continue to push the state of the art and try to make these aircraft quiet enough that even if they're flying over that same house every single time, we've shrunk the whatever you want to, you know, the single exposure level, 65 dB or whatever, to within the airport confines, or at least to the point where now only houses that have FAA retrofitted double pane windows and insulation are being exposed to these areas. So the work that we're doing is never completely resolved because that issue still persists, and neither of those is a good solution. Now, with respect to the UAM, where they have more opportunity to purposefully put vertiports, for instance. So they're looking at, you know, the cloverleaf on the highway or somewhere that's already a very high ambient noise area. And that's actually what you're seeing here is a sort of a heat map of noise in, I forget which city it is, but you're seeing basically the highways marked off here in the center of the city. And so they're looking at what happens when you fly high density UAM operations in an area that's already got high ambient noise. Do we actually affect a change to the ambient noise? Is it detectable? Do the people near those areas find that more annoying, or is it something that we can sort of sneak by with, so to speak? So hopefully that answers your question.
Yeah, that's interesting and challenging scenario. As I say, probably more work needs to be done to have a better or smarter way. Actually, I'm hoping that many of the tools you guys developing will help the commercial operator to propose better ways.
Mhm.
And simulation probably can also help us assess by simulating the different location, different background noise level. As you say, either knowing a few or a lot more, or spread out the pain. Hopefully, over time, people get used to it more so than before. And one thing I noticed that I made a note to myself that when we talk about the public services, sometimes we may need your help to when we approach and try to land at the emergency locations, we can cycle the rotor so they generate a louder noise, and we try to make it quiet so that folks on the ground can make sure they stay away from the landing site too.
Yeah, that was I think I actually got that some similar question at one of the venues that I presented this at, and is that or one of my interactions with the public, is like, well, it's the joke about putting a playing card in the spoke of your electric vehicle because they're too quiet in a parking lot. That we become too successful at making these things quieter. I think my response to that is, let's keep them from falling out of the sky in the first place. So.
No doubt. Yeah, keep it safe. Keep it quiet in general, and then we can always add a loudspeaker if we have to.
Mm-hmm.
Sounds good. Kurt, you have a question there?
Yes, thank you so much. Thanks for the presentation. Very impressive and needed in the public safety domain. I wanted to let you know I put something in the chat, and specific to the value of what you're speaking of is the need for advanced air mobility, part of the data reasoning fabric, digital twins, C5 ISR for public safety. Thank you, thank you, thank you. And then I also put in there a drive of public information on lithium ion from the fire department in New York and Underwriter Lab Fire Science Research Group. I think some of the, the biggest folder I've seen of good material on the subject. And then lastly is getting the word out to public safety. Johnny's aware that there's a group I'm working with that'll bring 30,000 firefighters together in April. If there's any opportunity to share some of this with some of the attendants there, I'd be happy to put you in touch. And again, thank you.
Yeah, I'd appreciate that. I may pass that on to our battery experts, but yeah, it's not lost on me the issue of how challenging lithium ion is to put out. I forget what the stat was for a car fire versus an electric car fire, but it was pretty striking. And so yeah, there again is in aircraft, as opposed to cars, which we can afford to make 6,000 or 7,000 pounds because they're you're really just overcoming inertia and rolling resistance. In aircraft, we can't afford that. We have to lightweight the structure in every way possible. And so coming up with clever ways to improve crash safety for batteries, not just for the aftermath, but most importantly for the occupants themselves, is a major challenge, and it's a major topic of research that we and industry partners are focusing on.
Thank you. And it's a bit of two parts. There's the lithium battery, but just advanced air mobility and public safety. I think the industry is thinking it's a long way off. And that's the part where if you wanted to share, you would be welcome so that they can start thinking about downstream advantages and/or problems, whether it's batteries or the advantages of autonomous flight, crewed or uncrewed, and how it will assist some of the 700,000 911 calls a day in America.
Mm-hmm.
Thank you.
Yeah, no, I'd certainly be happy to consider either myself or someone else representing our research there.
Other questions? I do have another one for you.
Mm-hmm.
Since you're the propulsion acoustic expert, let me ask a generic question that let's say for the electric multi-rotor distributed electric propulsion system that we commonly see on the eVTOL systems. Am I to assume that if a propulsor are highly efficient, tuned to be highly efficient, of course, matching the motor type, performance characteristics, and so on. Let's say the rotor itself combination are highly efficient from aeroacoustic perspective. Can I assume that a more efficient propulsor generate less noise because there's not enough energy wasted left over to create noise?
Yeah, so certainly one of the major aspects of it is just the way that an electric propulsor generates its torque compared to a gas turbine engine or an internal combustion engine, right? You're literally producing explosions in the engine to do that, and depending on what it is, you're still exhausting great amounts of air, and that in itself scales shockingly. I believe it's to the 8th power of the speed of the exhaust. So the noise, just a small reduction in how much you're expelling via the jet makes a huge difference in the overall noise. And that's how we've seen some of this improvement in jet noise over the year by moving larger amounts of mass slower in turbofans. And these aircraft, you're still fighting the issue of turbulence generated noise, right? So we're producing lift, we're disturbing the air. That there's no way necessarily around that. We do have people studying acoustically optimized rotor designs and trying to leverage different tools, the so-called MDAO, multidisciplinary design analysis and optimization tools to try to come up with a balanced design that balances necessary performance, because you require that propulsor to do some finite amount of lifting or thrusting, but you balance that with acoustics. Another challenge is actually inherent to the fact that you have multiple rotors now, and you have rotor-rotor interaction noise. So now you have rotor wakes interacting with each other. Your rotors are now interacting with the airframe itself, and some of this is, I'd argue, pretty inevitable. We're looking at different parametric studies of standoff distance from the structure, and different ways to reduce those interactions, but you can't totally eliminate those either. So it really is a matter of trying to understand the mechanisms, a sort of multi-pronged approach of understanding the mechanisms, coming up with an acoustic-centric rotor design shape, and vehicle configuration trade-offs that balance the necessary performance with the inevitable noise generation.
You're absolutely right. I mean, it's not a simple scenario, and everybody's almost many OEM has different configurations. Yeah, we even have tilt wings, tilt rotors, different rotor positioning, pretty complex or opportunities for different interactions.
And that's actually why you saw a lot of sort of varied, our focus has been on component level tests. What's not pictured here are some of our multi-rotor tests that we've done and continue to do, again, to try to understand the physics of the interaction noise that occurs, and how some of those parametric variations of placement of rotors with respect to each other, with respect to the structure, affect noise generation.
Sounds challenging. I'm glad that you guys are on it, and along with many other industry efforts and university efforts. So this is great. Really happy to see. I really thank you for the presentation, because it gives us across the board look at what NASA's multifaceted effort in all related fields. Sometimes we talk to specific branch and we get specific focuses. That's why I love your presentation very much so, because it gives us a broader, a better understanding of the different efforts in different areas. So it's good to know. It's good to know.
Yeah,
really,
well,
it's nice to know that our tax dollar at work in the right place.
Hopefully you're getting a bang for your buck, or less bang, a quieter bang. I mean, and again, when you say specific focus, this still only represents one of 7 projects across NASA that are tied to the activities that are under the umbrella of advanced air mobility. So it's quite an enormous task. Again, this sort of disruptive industry, and all of the different discipline groups that it affects, and all the different entities, the public, the local and state governments, and people that need to become stakeholders to make this thing a reality, and be accepted broadly. So
Sounds good. Again, appreciate your presentation, excellent presentation. And if no further question from our online members, if I know some of our members cannot attend online, they typically go to the recordings. And so if we have any information or questions or suggestions, want to establish dialogue, let me know. I'll make the
yeah, you've got
arrangement.
my contact. Yeah, you're welcome to send those on to me.
Sounds good. Sounds good. Again, thanks everyone for attending, and thank Devin for the excellent in-depth presentation. That will conclude today's session. Thank you again. Thank you, Tom.
Thank you.